Hi, everyone. I'm Aditya Shah, a fourth-year student at UT Austin. This presentation is part of a project for my Astronomy 364P course, which focuses on planetary systems. In this video, we'll take a closer look at a recent paper by Andrew Vanderberg and Joey Rodriguez that creatively uses the radial velocity method and some MCMC to put limits on possible companions, such as exomoons or binary planets, to the planets in the HR 8799 system. Before we delve into the details, what are exomoons and why do we care about them? Just like how exoplanets are planets outside of the solar system, exomoons are moons outside of the solar system. Starting with the discovery of 51 Pegasi b, which you can see over here on the left, by Michel Mayor and Didier Queloz in 1995, the field of exoplanet astronomy has exploded in popularity and relevance, and we've since discovered over 5,000 planets beyond the solar system. These discoveries have upended preconceived notions about the structure and formation of planetary systems, including our own. However, despite the ubiquity of exoplanets in our galaxy and the existence of over 200 moons in our own solar system, astronomers have not definitively found any exomoons, and instead we only have a couple of unconfirmed candidates, such as a possible companion to Kepler 1625b. Now, within the solar system, moons are really important, and they've garnered a lot of excitement for their role in the formation, structure, and evolution of the planets they orbit, as well as their potential habitability, ranging from the discovery of subsurface oceans on Europa, which we see over here, as well as another moon that orbits around Saturn, Enceladus, to the complicated role that they may play in their interactions with their planets, such as Io's role in managing Jupiter's energy budget. In addition to that, understanding the subtle nuances of natural satellites may lend themselves to solving open questions in giant planet formation and better understanding the occurrence rates of planets around different stars of different sizes. As a result, searching for moons outside the solar system can yield really unique insights and is ultimately a really worthwhile endeavor. So exomoons are really difficult to detect, and the objects that would be easiest to detect, such as large exomoons and binary planets, are very rare. And this is because the circumplanetary disks that would form the moon are typically much less massive than the planet. So there's just not enough mass there to usually form these super big moons or binary planets. And if you try and gravitationally capture one of those really big moons or really big binary planets, we know from previous work that it's typically pretty unlikely that that happens just from a probabilistic perspective. So on top of that, our current detection methods really struggle to have the sensitivities required to detect smaller moons, particularly those that are further away from the parent star. And so far, the direct imaging and transit techniques are the only ones that have really yielded generally reasonable constraints on the presence of exomoons or binary planets before this work. However, the radial velocity technique is something that shows a good deal amount of promise. So normally when we search for planets around stars using this technique, we measure the radial velocity of the star itself. So you can imagine this yellow circle is the star, while this blue circle is the planet. And we measure the wobbles of the star, which is the radial velocity method, by looking at how the spectral lines shift. In this paper, Vanderberg and Rodriguez use this method in a slightly different way. And instead of measuring the radial velocity of the star itself, they measure the radial velocity of the planet as it's being tugged on by the moon. So that's a little bit different from how the radial velocity is usually measured. It goes like one level deeper. Instead of using the radial velocity of the star to find the planet, they use the radial velocity of the planet to find the moon. So what data did they use in order to carry out this analysis? So in order to do this, Vanderberg and Rodriguez needed high quality spectra of the planets themselves. And luckily, members of the direct imaging community have developed the techniques and instrumentation needed to accomplish this over the past couple of years. And these advances have led to the availability of high quality radial velocity data for several planets over the past few years, such as Beta Pictoris b. In September 2021, a paper led by Jean-Baptiste Ruffiot studied the atmospheres and orbits of the outermost planets in the HR 8799 system, planets B, C, and D. And this paper included the radial velocity measurements for each of these planets with a precision of about plus or minus 1 kilometer per second. And these measurements were taken using the Arias instrument. Now, other groups had recorded other radial velocity measurements for these planets with somewhat comparable uncertainties, but they only reported one measurement per planet, and Vanderberg and Rodriguez wanted a little bit more than that. And trying to combine these different data sets could lead to some unintended side effects, because different instruments and analysis techniques could lead to systematic biases between the data sets. As a result, Vanderberg and Rodriguez chose to only use the radial velocity measurements reported by Ruffio in the interest of consistency. So at the surface level, the simplest way to find an exomoon using the radial velocity method is to try and tease out the periodicities in the radial velocity signal using a periodogram, a plot that kind of decomposes the dominant frequencies within a signal using a Fourier transform. Then it's possible to determine the false alarm probabilities for the periods within the periodogram. If the false alarm probability is above a certain threshold, it's a pretty good sign that the exomoon doesn't exist. And if it's below a certain threshold, it's a pretty good sign that the exomoon does exist. Now, beyond this, Vanderberg and Rodriguez also use a technique called Markov chain Monte Carlo, or MCMC, to place upper limits on the presence of companions to these planets in the HR 8799 system. A Markov chain is a probabilistic model in which the probability of any event depends solely on the event before it. And a Monte Carlo experiment relies on repeated random sampling. So MCMC combines these two ideas to randomly sample a vast array of states in which the next state depends only on the current sample. The MCMC model tests different model parameters by essentially wandering around this parameter space, and then it checks their goodness of fit. And the reason this is special is because it not only finds the best solution, but it also maps out the uncertainties in the solution, since it's exploring so many different things within the parameter space. And MCMC's ability to get solid uncertainties has really allowed it to grow significantly in popularity and relevance, particularly over the past several years. So Vanderberg and Rodriguez first looked at the radial velocity signals from Ruffio's paper. They didn't see any obvious signals, and the false alarm probabilities for HR 8799, B, C, and D having moons around them were about 68, 49, and 15% respectively. So this kind of surface level analysis isn't yielding that much. There's no obvious radial velocity signals for a moon. So if we can't find anything obvious, maybe using that MCMC stuff, we can try and get some clearer limits on what may or may not exist. Now, since the raw radial velocity data did not yield any clear companions, Vanderberg and Rodriguez used their MCMC model, which gave the limits that are shown on this slide. The background shading shows the probability distributions of the allowed companion minimum masses as a function of orbital period. The dark, medium, and light purple lines show the 1 sigma, 2 sigma, and 3 sigma contours as a function of the orbital period. The gray lines show the boundary between a binary system and a planet-moon system, aka is our companion a binary planet or a moon? Objects below the gray lines are moons, while those above are binary planets. So they find, looking at all of this data, that for all 3 planets, we can rule out the vast majority of companions with minimum masses greater than about 2 Jupiter masses in periods shorter than 5 days. And you'll notice that the constraints are stronger for shorter orbital periods, since the radial velocity signal will scale with the inverse cube root of the period as per Kepler's third law. And the relatively sparse sampling of the radial velocity observations makes it difficult to accurately determine longer period signals just because there isn't quite enough data. So putting all of this together, what does it all mean? Here are the key punchlines. The first really important thing to note is that although they didn't actually find any moons or binary planets around these planets in the HR 8799 system, the reason this is important is because this work shows that we can use the radial velocity method to place meaningful limits on companions to planets, which had never really been done before. On top of that, this work also explores a parameter space that is different from previous work trying to place limits on exomoons and binary planets. Transits tend to favor planets that are really close to their stars, since the transit probability for that planet will scale with the inverse of the semi-major axis. So closer in planets are more likely to transit. So naturally, when we observe things with transits, we have this bias towards trying to find things that are close to the star. And now direct imaging is a little bit better in that regard, in that it can observe planets further away from the planets, from the parent stars. But when we're trying to find constraints on the moons that it's looking at with direct imaging are also going to be far away from the planets. This radial velocity technique is unique in that it allows us to explore moons that are in close orbits that are around planets that are far away from their parent stars, which is something that the other techniques cannot really look at. And the final point that I want to drive home here is that the radial velocity data used in this paper are not particularly precise, as they were collected by an instrument that was not truly designed for this kind of work. But in the future, multiple new instruments and upgrades are coming that will hopefully make it possible to detect Neptune mass or even rocky moons in the near future. And all in all, as spectroscopy becomes more and more prevalent to study exoplanet atmospheres and compositions, the library of high quality available radial velocity data for exoplanets is only going to continue growing. And with this data, hopefully we can make even more interesting inquiries into the prevalence and occurrence rates of exomoons and binary planets that can ultimately help us get to the bottom of planet and satellite formation in our universe. So here I've got some of the references that I have in my presentation. And if you have any questions, feel free to leave a comment or reach out to me. Thank you and have a great day.